and welcome to today's lecture. Today we will talk about applications of path cycles and all that. So in the beginning of the course I promised you beautiful theory and useful applications. We've seen the theory, now come the applications. So we'll see 4 different applications. The 2 first we'll go through in some detail, and the 2 last ones will be just an overview. So let's start with the first application, that is the shortest path problem. So the idea is that you are in a sort of city or a setting where you have multiple paths between some interesting points, and you want to find a path of the least length, or maybe if paths cost money, the least cost or the least time, or if you have some other setting, some other quantity you want to minimize along the paths. The application is delivery cost or logistics. So assume, for example, that you live in city A and you want to travel to city B, and there is a direct flight, but it's extremely expensive. So you have options to fly to other places in between. They are less expensive, so how to find the least costly route, and so on. The mathematical model of this is the usage of weighted graphs, and this will be the case for all the applications today. So a weighted graph is a graph such as the one you see here. So it is just a normal graph with the additional data of a number on each edge, a positive number representing the so-called weight of the edge. So in applications you use sometimes a sloppy language where you talk about shortest path. What you mean by shortest is not smallest number of edges, but the path of the least total weight. So for example, if I take this path that goes along the upper part of the graph, the length of this path is 3 plus 2 plus 5, 10, whatever units I am using. So weighted graphs are the way to model this situation. So how do we solve this problem? Well, we're going to go through an algorithm. So what do I want to do? I want to find the shortest path from A to B. Maybe there are several paths, but I want to find one of minimal length or weight, whatever you want to call this thing. And the way to do it is I'm going to go through the vertices and I'm going to assign them a value that corresponds to the length of the shortest path from A to that vertex. As I go through the vertices and end up in B, I will be done with my path. So there is a specific algorithm for this, and this is called Dijkstra's algorithm. So Dijkstra's algorithm is named after Dijkstra, who was born almost exactly 90 years ago. And it goes like this. So these 5 steps are the ones you repeat for the argument. Let's see how they work with this illustrative example. So what we want to do is to find a path of shortest length or lowest cost from A to B. So you start at value, and remember the way to do it is we want to go through all vertices and assign to them values that tell us how long is the shortest path to this vertex. So we start with A. The shortest path from A to A has length 0, so we assign the value 0 to A. Now we go to all the vertices that are adjacent to A, and we assign to them the value of sort of the length of the path from A to these vertices that only uses one edge because they are adjacent. So from A to this vertex, if we go straight, this will cost us 1 unit or take 1 hour or be 1 kilometer long, depending on what this one represents. I will call this the length. So the length of this one is 1. The length of this edge is 3, meaning that the path, this particular path from A to this point has length 3. And the length of this path from A to B is 17, so I add 17 to 0, I get 17 here. These are not necessarily the shortest paths, but these are the paths I get if I go the direct route from A to these vertices. Now I look at, among the red numbers I now have, which one is the smallest. It's this number 1. This tells me that this vertex cannot be reached by any shorter path, because any other path would have to go through, starting from A. If I don't go directly here, I have to go through some other vertex adjacent to A. But to go there, I would have the length 17, or to go there, I would have gone the length 3, which are both greater than 1. So now I'm confident that my 1 is the best possible for this vertex, and I make this 1 permanent. Now, starting at my permanent vertex, I do the same as I did with A. I look at the adjacent vertices and I assign new values to them. So, if I now, having arrived to this point, if now I want to go to B, then I add the length of the remaining road, which is 12, I get 13. 13 is much better than 17. So happily, I forget about my 17 and write 13, my new best possible for a route from A to B. This vertex has no value yet, so let's see. I have here 1, and then 1 plus 4 is 5. This vertex already has the value 3, but maybe I can do better. So from 1, if I add the length of this road, which is 4, 1 plus 4 is 5, but 5 isn't better than 3, so I don't change the value. I already have a shorter route to this point. In other words, I calculate L of V for all the vertices adjacent to my blue vertex. I calculate this value like that, and I update it if I decrease the value that was already there. So here I had such a decrease, here I did not. Here there was no value from the beginning. Sometimes people put the value infinity at the beginning to just keep in mind that this needs to be improved, or you don't put any value, you just adjust the value now. Okay, now I go to my next red vertex. So of all my red vertices, I go to the one with the smallest number. By the same reasoning, it is this vertex which has value 3. There is no route shorter than 3 to this vertex, because all other routes either have to go through vertices with higher value, or I've already examined them and excluded them because they would have given me a higher value. So now I'm confident that this vertex cannot be reached any shorter. I make this value permanent. So I'm doing step 3, I'm repeating step 3 here. And then I do the same for this vertex. I look at all the adjacent preliminary vertices and see if I can improve something. So from this vertex of value 3, I can reach this vertex by adding 2. 3 plus 2 is 5. I already have 5. No improvement. So I'm done. I go to the next vertex with the lowest red number, which is this one with value 5. By the same reasoning, I now know that 5 is the shortest path to this vertex, because any other path would have to go through some vertex with a higher number, or I've already excluded that path because I have checked the vertices with lower number. So now that I have made this value permanent, I look at all the adjacent values. So the only adjacent vertex left that is red is B. So if from 5 I add 5, I get 10, which is even better than my previous 13. So I change the value of B to 10. Now I go to the vertex of the lowest red value. Well, there's only one here. I make it blue. I make the value permanent. And then we're done, because now I have a value for B. So when I have reached B and given B a permanent value, we are done and we stop. Obviously, for this particular graph, maybe by just looking and not using this algorithm, you would have found the shortest path or the smallest value immediately. But of course, in general, this is an algorithm that can work for graphs with 10,000 vertices. And there, of course, you cannot see things immediately. The algorithm works in general, and this example illustrates how it works. So now I know that the shortest path from A to B has length 10. But the algorithm has not produced a path. I mean, maybe you can see it for this small graph, but in general, I don't know which path to go. So how do I find the shortest path? Well, the answer is you trace back from, sorry here, not V, but B, along edges whose weight is the difference of vertex value. So let me explain. So here I start at B. I have my value 10. Let me use a different color. So I have the value 10. Which was the last step of the journey? Well, it cannot have been this 17 one, because there's no way this can have given me 10, nor this 12 one. So it has to be this one. So the length of this, the weight of this edge is exactly the difference between the previous path and B. So this is one way to sort of keep this economical. I'm not taking more steps since last than I need to. Both 0 plus 17 and 1 plus 12 are greater than 10. So this is the last step of the path. Then I go back. So now I have this vertex V. And now I ask myself again, which steps which could the previous step have been? Well, it must be a step where the weight of the edge is exactly the difference between the values of the vertices. And here there are two possibilities. So I could have gone this way, because 2 is 5 minus 3, or I could have gone this way, because 4 is 5 minus 1. So there is no waste. The weight of the edge is precisely the difference. And then the last step is clear, because I have this one and I have this one for that other one. So in this case, we had two different paths, the upper path and this zigzaggy path, that both had length 10. And in general, I'm not interested in finding all of them. I just want to find one path that gives me this shortest way of getting from A to B. And I find it by this backtracking. So I start from B and I go back along edges where the difference is exactly the weight of the edge.